Okay, so we're happy to have Aaron Schild with us. He's our new postdoc, or I guess the first optimization postdoc. Hopefully we're going to continue this thing. He's going to tell us about algorithms and hardness for linear algebraic problems.
Hi everyone, thanks for coming and thanks for waiting so long with the mishaps. So today I'll tell you about how to do spectral graph theory quickly on a special class of dense graphs. And also at any point, please let me know, or please interrupt me if you have questions. So there are a few different ways to motivate these problems, but let's sort of the classic way to look at this. The classic problem is what's called the n-body problem. So in the n-body problem, we're given n points in R3, and we'd like to compute the gravitational force exerted on each point by all of the other points. So for example, we'd like to say compute the amount of gravitational force on Mercury due to all of the other planets, which are obviously not in the right locations here. But so being computer scientists, let's not look at R3 and let's instead look at D dimensions. So we can, in particular, and also let's simplify the problem a little bit. So instead of actually computing the force induced by all of the points on each individual point, let's just instead compute the sum of the magnitudes of those forces. This quantity is meaningless, but it's essentially equally difficult to compute to the actual force vector. So essentially what we want to do is, given n points in Rd, we'd like to compute the sum of 1 over the distance from a point to all of the other points. So at the beginning of the talk, I mentioned that we should think of this as a problem on some sort of graph. So let me now state how you think about this as a graph problem. So first, let's define the function f of z to be equal to 1 over z. So throughout the talk, I'm going to use this definition. And then given this function f, we'll define a graph on the set of points x. This graph has vertex at x, and there's an edge between any 2 points in x with weight f of the L2 distance squared between them. And then our problem is just we want to multiply by the adjacency matrix of this graph. So given a vector, we'd like to compute the adjacency matrix times the vector. So one naive way of doing this is just let's write down the matrix A, the adjacency matrix of the graph. And then after writing down the graph, we'll compute this matrix vector product. But that's not very good because that takes quadratic time. That takes order n squared time. And we'd like to figure out if it's possible to obtain almost linear time algorithms for this problem. Any questions about the motivation or the setup? Yeah.
So why isn't this an all pairs graph? So is it an all pairs graph? Like so there's one edge for every pair. Sorry.
Yes.
So it's a fully dense graph.
Yes, it's a dense graph.
Yeah. Okay.
Yeah.
So right. Yeah.
Yeah, you just want to compute this up. Yeah, Farzan?
So you study this problem in the unweighted case. All the masses are the same.
Yeah, the masses don't. Yeah, when masses are arbitrary, it doesn't really make the problem any harder. Yeah. Other questions? Okay, so there's this classic algorithm for this problem dating from the 80s called the fast multipole method. And basically what this algorithm is it's a way to solve this problem in near linear time in low dimensions. So specifically, given n points in d dimensions, it's possible to compute a matrix vector product approximately in a log of 1 over epsilon to the d times order n time. So the way to think about this result is you can, for very high amounts of accuracy, you can solve this problem in subquadratic time in low dimensions. So this algorithm generalizes to some other functions f as well, which I'll talk about a little bit later. But one thing you might be a little bit annoyed with in this runtime is that this runtime is exponential in D. This runtime suffers from the so-called curse of dimensionality. And throughout in the second part of the talk, we're going to look at this quite a bit. But before I move on, let me mention that if you care about substantially less accurate algorithms, where epsilon is just a constant rather than 1 over poly n, then you can get something that doesn't depend exponentially on D. And this was due to some recent work in last year. So for the rest of the talk, I'm going to start by going through the fast multipole method in greater detail. So I'm going to, for those of you who haven't seen the fast multipole method before, I'm going to tell you how it works for this function. And then, afterwards, we'll look into whether this exponential dependence on D is tight. And we'll show that it actually is, given a strong exponential time hypothesis, a popular conjecture in complexity theory. And then at the end, I'll talk about some other results that we proved in this work and some open problems related to this. Any questions before I go through the fast multipole method?
You're saying exponential dependence either on D or log 1 over epsilon. So either your polynomial is 1 over epsilon or exponential.
So if you are fine with epsilon being constant, then you can get a near linear time algorithm that has runtime something like poly D times poly 1 over epsilon times n. But if you want a polylogarithmic dependence on 1 over epsilon, then you need an exponential dependence on D. I'm not sure. Yeah, we can talk about that more after, yeah.
In obviously with planets and things, we are thinking of low dimensions. Are there particular applications you have in mind in the high dimensional case, or?
So there's, this work was motivated by this problem called kernel density estimation, where you have some function. I think it's a popular primitive in machine learning, but I don't know that much about it. Yeah, we can talk later if you want. Okay, so let's talk about the fast multipole method. So let's just recall what we want to do. So we're given so let's generalize a little bit. So instead of just having one set of points x, we'll have two sets of points, a and b. So in particular, we like to compute the force induced by a set of points b on another set of points a. So what this amounts to is we want to compute for every point in the set A, we'd like to compute the sum over b of h of the L2 norm squared between A and B. So, the way we'll do this with h is equal to f is as follows. So we'll start by assuming that h is a low degree polynomial and seeing how you can do it in this case. And then we'll use that subroutine to get the desired kind of approximation, the desired runtime, when A and B have special structure, when A and B consists of well-separated sets. And then we'll see how you can apply this to get the general case, when A and B are arbitrary sets of points. So the way I'm going to present this is a little bit different from the classical fast multipole method, which uses a slightly different polynomial approximation to the function, but I'm going to present it this way just because it's a little bit easier to present. Okay. Okay, so let's start with the first part. So in this part, we'd like to approximate this. We like to exactly compute the sum over b of h of a minus b 2 norms squared. So let's, for the sake of simplicity though, let's just, let's replace the L2 norms squared on the inside with an inner product. So our goal is just the following. So if h of z is equal to z to the t, we just like to compute the sum over b of h of a inner product b. So some of you probably already recognize how you do this in near linear time or efficiently. And this is using what's called the kernel trick. So the idea is that a inner product b to the t, it can be written as the inner product of g of a comma g of b for some embedding g into high dimensions. And specifically d prime, the dimension that you embed in, it's at most t to the order d. So the way you should think about t to the order d here is that t is a small number, say a constant, and d is substantially smaller than log n. So this is a small number. So just for those who haven't seen the kernel trick for a while, let's just do an example. So the inner product of two two-dimensional vectors cubed, you can, if you just expand it out, it's equal to that. And this quantity can be written as the inner product of two four-dimensional vectors, where each vector just depends on a and b separately. So the key observation here is that, so now let's use this trick. So the key observation is just that the sum of these weights is equal to g of a inner product, the sum over b of g of b. And the reason this is useful is that we can use pre-processing to compute this sum of the over b. And then after we do that, we just take the inner product with each of the embedded vectors from A. And then that gives us all of the inner products that we need. And that took t to the O of d times n time. Are there any questions about how to, about this, how to compute? Yeah. So G, so in general, you would obtain G by doing a multinomial expansion.
Is it just a tensor product of the vector with itself?
I'm not sure off the top of my head, probably it is.
That's the...
Those constants wouldn't show up.
No, I mean, this is you're using this identity that the dot product to the k is like tensor product to the k, like k tensor product dot products.
Okay. It's probably, yeah, I think it's the same thing. Yeah. Okay. Any other questions right now?
Is the only thing you used here that the matrix is low rank?
Yes.
This just works for any low rank.
Sorry?
Just works for any low rank matrix, not just this one. But.
Well, the fact that the h of z is equal to z to the t means that the matrix ends up being low rank. Yeah. Yeah.
What's the matrix? Just the
Matrix is h entries.
Yeah.
Any other questions right now? Okay. Okay, so now we know how to do this multiplication when h is a polynomial. Let's now do it when, let's try to get back to the function that we're actually interested in, which is this function f, which is 1 over z. So, so a natural approach to try is just let's Taylor expand f. And then let's cut off the Taylor expansion at some point. and then do the multiplication on the resulting polynomial. So unfortunately, though, in general, there's no polynomial f that there's no polynomial p that approximates f everywhere. So how do we get around that? Well, there is a polynomial, or there are polynomials that approximate f on a small interval. So let's just use that. So in particular, if the sets A and B are well separated, then the distances all lie in some interval, where the ratio between the max and min endpoint of that interval is a constant. So then,
Sorry, is that the definition of well separated? Or what is well separated?
yeah, so we're going to say that two sets A and B are well separated if the the minimum distance between the sets is at least rho times the diameter of either set. So if A and B are well separated, then all of the distances lie in this interval. So approximating f with a polynomial gives a good enough approximation. So in particular, if this polynomial has degree log of 1 over epsilon, so the runtime of this is log of 1 over epsilon to the d times the total size of the sets. And this is the kind of runtime that we wanted. But we have this assumption that A and B are well separated. So let's try to get rid of that assumption. We'll get rid of that assumption using this very classic tool in computational geometry called the well-separated pairs decomposition.
The error here depends on this row. So what is the dependence of? So this row, this row controls the well separation, and the Taylor expansion there is an error which.
Oh, so rho. We're applying rho here with rho is equal to 3. So the claim is that on the interval r comma 3r, there's a function that epsilon approximates f there's a polynomial that epsilon approximates f with degree log of 1 over epsilon. You just take the Taylor expansion and chop it off after log of 1 over epsilon terms.
And what if you said rho to something else? Can you say what you would get?
So you would get, let's see. I don't think you would get anything better, but I can talk about that with you afterwards if you want. Any other questions about the well-separated part? Okay, so let's try to apply this. So the way the fast multipole method applies this is by using what's called a well-separated pairs decomposition. So in a well-separated pairs decomposition, what we want to do is the goal of a well-separated pairs decomposition is we want to write the set of pairs of points in the set X that we want to decompose as a union of pairs of sets. So we want to write pairs of elements. We want to associate pairs of elements with pairs of sets. So in particular, these pairs of sets have the property that each pair is well separated. And furthermore, each pair of elements should be covered by exactly one pair of sets. So one naive way of making a well-separated pairs decomposition is we just make a separate pair for each pair of elements. But this is a pretty dumb well-separated pairs decomposition because they're n-squared pairs. It'd be better if we had a near linear number of pairs. That's the goal here. So there's this classic theorem from the 90s that gives you such a well-separated pairs decomposition. So given any set of points in d dimensions, you can find a well-separated pairs decomposition in near linear time for d sufficiently small. in which each vertex participates in a small number, in a near constant number of sets. This is also assuming, so throughout this talk I have this parameter alpha. Alpha is the ratio of max to min distance. So this is always when alpha is polynomial, when the ratio of max to min distance is polynomial.
Obviously, the original algorithm didn't use this theorem since that's from 87.
Yeah. So the original multipole method used I think a different decomposition, that mostly like some sort of just cut space into grids. I don't remember exactly what the original thing was, but yeah, that's right. So what I'm presenting is a little bit different from the classic multipole method, but it's very similar.
Would you say this? How to do this?
Yes. Yeah, that's on the next slide. Yeah, so the way you construct this well-separated pairs decomposition, so if you don't understand this construction, it's okay. It's not super directly important to the rest of the talk, but I'll go over it here anyways, in case you're curious. So you start by making a quad tree on your point set. So what that means is you just cut. So you let's say that our space is bounded in some box. We're just going to cut that box into boxes with half the side length. And then just to save space, we'll not recur on boxes that don't contain any points, because we don't need to. That's what the compressed refers to. So we'll start by making a quad tree. And then given this quad tree, we'll now construct the well-separated pairs decomposition. And the way we'll do it is we'll use recursion to do it. So specifically, we'll, given two sets A and B, we'll construct a well-separated pairs decomposition on them by doing the following. So if A and B are well-separated, then we'll return the pair. We can add this to our well-separated pairs decomposition. Otherwise, we'll split up one side of the pair. We'll split up A using the children in the quad tree, and we'll recur on those sets. So the idea is that you start off with two sets that are not well separated, and through repeatedly chopping up the sets, you eventually get to pairs that are well separated. And the key thing about this recursion is that each pair of elements, you're always preserving the invariant that each pair of elements is covered by exactly one pair of live sets. Are there any questions about the construction?
How do you decide how to split a set into two parts?
So you split the set using a quad tree, using the quad tree. So each of these, so each node, so the quad tree is a tree where each node of the tree is associated with some subset of nodes in X, and it's hierarchical. So a child set is contained in the parent set. So what we'll do is, so we start at the top of the tree by calling the algorithm on the pair x comma x, and as we go, the recursion goes down until you get to a pair of sets that are well separated. And if a pair is not well separated, you split up one side of the set. And the way you split it up is using the quad tree. Did that answer your question at all?
I don't know what a quad tree is. So
Oh, sorry. So
I don't know what property the quad tree has that makes this decomposition.
Okay. Yeah. So a quad tree is. So let's just look at two dimensions. you construct a quad tree by starting with your set of points, make a box that contains all of the points, and then repeatedly split each square left over into subsquares with half the side length. So for example, let's just...
It's exactly this picture. So in d dimensions, it would be...
2 to the d. Yeah, exactly. And then, so the... let's see. Does that address your question at all, or? Okay. Any other questions? Okay. Okay, so now we have this well-separated pairs decomposition. Let's use it to do this matrix vector multiplication. So the way we're going to use it is we're going to write our matrix, this F matrix that we want to multiply by, as a sum of matrices defined over well-separated pairs. And then we have an algorithm that handles well-separated pairs already.
Can you just think of the whole algorithm as finding a low-rank approximation to the original matrix?
Yes. Yes. So, yeah, so you can write this matrix as a sum of, so the reason you can write this matrix as a sum of these other matrices is because of the coverage property, the fact that every pair of elements is covered by exactly one pair of sets. And then so we can apply the well-separated subroutine, and that gives you an algorithm with this runtime. And because of the fact that the well-separated pairs decomposition is small, it has an order n number of sets, the total runtime is the desired runtime, log of 1 over n over epsilon to the d times n. So this completes the multipole method. Yeah?
I thought there was like almost coverage, like each pair was present in like a small number of sets, but not exactly one.
Each element is in a small number of sets. Each pair is an exact number.
Okay.
Yeah.
Gotcha, sorry.
Yes. Yeah.
So I was just thinking about the low rank idea. Since you have this low rank, this ability to do matrix vector multiplication, should I think about this as a approximation to the matrix in like which norm, in like spectral norm then, or?
So I'm not sure off the top of my head which norm is the right one, but it has the property that, the key property that's relevant is that if you look at m times the all ones vector, its entry-wise 1 plus epsilon approximately the same. Yeah, so
It's kind of like infinity norm maybe then.
So yeah, so if you apply this for vector, if the ones vector were replaced with vectors with negative entries, then I think it would be the infinity norm.
Yep. Thanks.
Other questions? Okay. So just to recap, so the fast multipole method, what it did is it started by building a well-separated pairs decomposition, and then it used that well-separated pairs decomposition to write the matrix as a sum of matrices defined for well-separated sets. And then you can Taylor expand the function, and by Taylor expanding the function, you can write that, you can approximate that matrix with a low rank matrix. With rank like log of 1 over epsilon to the d. Okay, so this is the fast multipole method. So one thing that was a little bit annoying about it is this exponential dependence on d. It doesn't work well in high dimensions. So one question is this actually necessary? Is this exponential dependence on D necessary? And our main result that I'll tell you about is that assuming the strong exponential time hypothesis, it is. And again, if you only care about constant epsilon, you can approximate this efficiently. Okay, so for this next part of the talk, I'll go over how you, or I'll talk about how you show that SETH implies hardness. So before we talk about the reduction, we need to talk about the hypothesis that we're depending on. We need to have shared beliefs about complexity theory, or at least suspended beliefs about complexity theory. So the strong exponential time hypothesis is a statement about algorithms that solve KSAT. So in particular, let Sk be the minimum value for which a 2 to the Sk times n time algorithm exists for solving KSAT. So in particular, just to get a feel for things, S2 is equal to 0 because there's a linear time algorithm for solving 2SAT. The exponential time hypothesis states that S3 is strictly greater than 0. And the strong exponential time hypothesis is about k approaching infinity. So one thing you might wonder is, well, why don't we just ask S3 to be equal to 1? Well, it turns out that there are non-trivial algorithms for KSAT. In particular, S3 is strictly less than 1. This is a result due to Paturi, Impagliazzo, and Zane. So instead, we can really only ask about the maximum of all of these SKs. So the strong exponential time hypothesis essentially says that you can't solve SAT in less than 2 to the n time, where the constant in front of the n is 1. So the strong exponential time hypothesis has a lot of implications for complexity theory. And in particular, one implication that it has is related to this problem called nearest neighbors. So specifically, we're going to, in our hardness results, we're going to reduce from the bichromatic nearest neighbor problem. So this is the problem. This is the following problem. So in this problem, we're given two sets A and B, and we'd like to compute the minimum distance between any points in A and B. So this has been the subject of a lot of work, and in particular, there's this celebrated work by Indyk and Motwani that started the line of work on approximate nearest neighbors, and showed that you can C approximate this quantity, this minimum distance, in order n to the 1 plus 1 over C time. And it was recently shown by Aviad Rubinstein that this dependence on C is at least somewhat fundamental. You need some dependence on C up there, in the sense that for small epsilon, 1 plus epsilon approximate bichromatic nearest neighbors requires almost quadratic time. So this is a conjecture that we'll be reducing from. So any questions about the beliefs that we're going to have for the next 20-ish minutes? Okay. So let's first see, so instead of directly showing hardness for the function that we care about, let's instead show hardness for a much simpler function, a much easier function. And in particular, the relevant property of this function is that it decays very rapidly. So specifically, the way we're going to solve approximate nearest neighbors using this multiplication by this function is as follows. We're going to first make a graph on the set A union B, and then where edge weights are given by H, And then we're going to use our subroutine, use our matrix multiplication subroutine to compute the cut size between A and B. I claim that you can do this in one multiplication. And then, given that information, we're going to threshold. So in particular, it's possible to show the following. If the closest pair in A and B has distance at most k, then the cut size is high. The size of the cut between A and B is high. And then so that's the completeness case. In the soundness case, when the minimum distance is high, you can show that the cut size is small. And in particular, the reason why the property that we're using about H in this reduction is the fact that it decays so quickly. In particular, if the minimum distance is at least 1 plus epsilon times k, the total size of the cut is is n squared times some value that's much smaller than k to the minus log n. So there's a gap between these two settings. Are there any questions about this reduction? Okay. Okay, so that was for a function h that is rapidly decaying. But f of z is equal to 1 over z is not so rapidly decaying. So the question is, how could we show hardness for this? And what we'll do is we'll try to use our f multiplication algorithm to get access to a multiplication algorithm for a much more rapidly decaying function. And specifically, we'll do that by using linear combinations to take derivatives. So the basic idea is as follows. So we have these two sets of points A and B in d dimensions. So what we like to do is we like to compute. So we'd want to multiply by the f prime matrix. Or actually, we like to multiply by the kth derivative matrix. So if we had an efficient way of multiplying by the kth derivative matrix, we would be done, because the kth derivative of f is 1 over x is proportional to 1 over x to the k plus 1. And if k is equal to log n, then that's a rapidly decaying function. And we've already shown hardness for that function. So just to give a simple example of how you access the derivatives, let's see how we would multiply by the f prime matrix. So the way we're going to multiply is we're going to create two sets of vertices. We're going to take the points in B and make two sets of vertices, B0 and B delta. And specifically, B0 is just going to be the set of coordinates where you tack on a 0. And B delta is just going to be the set where you tack on a delta. And so let's let n0 be the matrix, the f matrix for these points, and let n delta be the f matrix for these points, the matrix that we want to multiply by. So the claim is that the matrix that we want to multiply by the f prime matrix, this is just n delta minus n0, or it's approximately n delta minus n0 divided by delta squared. And the reason this is just because the entries of this matrix are f of a minus b 2 norm squared plus delta squared. And the entries of this matrix are just f of a minus b 2 norm squared. So this is just an approximation to the derivative. Okay, so using a similar trick, you can show that you can get access to the kth derivative by doing k plus 1 of these matrix vector products. So therefore, if you had a subquadratic time algorithm for that, you would get a subquadratic time algorithm for the kth derivative. And this shows hardness only for the exact case. But a generalization of this works for when you want log of 1 over epsilon, dependence on the error. Are there any questions about the hardness proof? Okay. So just to summarize, we showed that no algorithm can multiply by the F matrix unless in subquadratic time, assuming SETH. And the way we showed that is by reducing from approximate nearest neighbors. So it was shown last year that approximate nearest neighbors is hard for sufficiently small epsilon. So given that fairly directly, you can show hardness for multiplying by rapidly decaying functions. And by taking a linear combination of a small number of matrix vector multiplications, you get access to a rapidly decaying function. So now I've talked about hardness. Now I'll talk a little bit about some open problems. So our work. In our paper, we have more general results than what I stated here. So in particular, the kernel trick shows that constant degree polynomials lend themselves to fast multiplication algorithms. We can essentially show that if a function f is not approximated by a polynomial with terms below log n, then it's hard. So we have something that essentially solves the high dimensional case when d is at least log n, but we don't know much about the low dimensional case. In particular, when can you do something like the fast multipole method? When does the fast multipole method work? So for example, in this talk, the methods in this talk generalize fairly easily when f of z is z to the c for some constant c. And also it generalizes to the Gaussian kernel. But there are functions that the multipole method definitely doesn't work for, assuming SETH. One example is that of threshold functions. And but we don't know that much more than that. In particular, one function that probably looks extremely stupid, but it would be nice to know a little bit more, I think might be a useful case to look at, is f of z is equal to cosine of z. Yeah.
So if you did this over the complex, like complex multiplication, why is it different from powering? That's because I'm usually thinking of like in FFTs and things, cosine and powering are kind of related and similar. It's just, yeah.
So I guess it would be nice to be able to work with complex numbers, but I guess I don't know, like when you're looking at functions of distances, it's sort of weird to allow complex numbers in the argument. Yeah, so it would be really nice if we could just directly work with complex numbers somehow, but I'm not sure. It'd probably be simpler to prove hardness and stuff if you could. Any other questions? So in addition to this problem, we also looked at some other problems. We also showed some results for spectral sparsification and solving Laplacian systems. And in particular, the kinds of functions that are amenable to sparsification are ones that are multiplicatively Lipschitz. So these are functions where where for any constant c, f of cx is at most c to the L times f of x. So we show that if this is the case for your function, then you can sparsify it efficiently. So we looked at these problems, but there are a lot of other problems that people have looked at and also are open in this space. So in particular, it'd be nice to know if there are good algorithms for exact max flow on graphs like this. Some problems that have been looked at are things like min-cost matching. A min-cost perfect matching. And another problem that people have looked at is this problem called the geometric transportation problem, which is essentially finding an L1 minimizing flow in a geometric graph. And for this problem, we have algorithms that have a dependence on epsilon that looks like epsilon to the exponential in d. Sorry, not delta. D. But it would be nice to know if you could improve this dependence on epsilon to log of 1 over epsilon using something like multipole. Okay. Yeah, so are there any questions? Yeah.
Can you explain your sparsification in more detail? Like, so you can come up with a sparse matrix that you can compute f on that matrix and get an approximation.
So this is like cut sparsifying or spectrally sparsifying. So the point is that you can sparsify the graph in n to the 1 plus little of 1 time for functions f that are multiplicatively Lipschitz. Yeah. And yeah, you can talk more offline about it if you want. Yeah.
So I'm just wondering about this, which things are amenable. I mean, do any of these results, I guess the order of your polynomial is sort of the most important thing that you showed here. Do you have any like results for functions like, where you have like just more general smoothness assumptions like decay rates of higher order terms or something like that? No.
So essentially this reduction that we have here allows you to access the log nth. It allows you to show that if you have access to a multiplier for your function, you can access just the polynomial, like something like the polynomial truncated at the tth order, where basically you can, if you have access to your function, you also have access to a function that just has higher order terms, or like t and higher order terms. But yeah, I'm not, but that's not enough to show hardness for multipole though. Yeah. Any other questions?